Hello everyone, this is Athreya and welcome to our channel CodeChef. Today we're going to be solving the problem ADAKNG with the code ADAKNG and the difficulty level of cakewalk. So let's get started. Here it's given that Chef is training her calculation skills and she's trying to place the king on a chessboard. Remember the chessboard has 8 rows and 8 columns, and the rows are numbered from 1 to 8 and the columns also are numbered from 1 to 8. The square is denoted by R and C. A king from RC can move to another square R dash C dash only if this condition is satisfied. This is nothing but, for example, let's take the small grid, subgrid here. So there are 8 rows and 8 columns, but we are just taking a small grid for example. Let's say the king is here. If the king is here currently at cell R, C, that means that the reachable cells from this king are directly above. In one move, it can go here, go here, go here, go here, go here, go here, here and here. So there are 8 possibilities for the king to move after one move. The king can move up, down, left and right and all the diagonal directions also. So 8 possibilities for the king. Of course, if the king was placed here, these possibilities are not valid. There's no up, there's no right. For any valid cell here where the king is placed in one move, it has 8 possibilities. It can move up, right, left, down, all the diagonals like this, 8 possibilities. This is what this condition is telling, that from RC, if the middle is RC, then all these cells that are highlighted, these 8 cells around it are R dash, C dash, where R dash, C dash are reachable from RC. Basically, this equation is telling us what cells can the king move. And now, for example, if I take a little larger grid, for example, let's take this example. Let's say the king is here. If the king has to move here, it cannot do in one move. It has to you do 2 moves. It can go diagonally here and diagonally here also. It can go right and right also. It can go like this also. It's like 8 switch. But there are many ways to reach here. But you cannot reach here in one move. Basically, in one move, the king can go to one of these 8 surrounding cells only. So that is the important part to note here. Now you know how the king moves. Let's look at the question. Ada has placed her king on R, C and she's counting the number of squares that can be visited or reached by the king in K moves. Like I said here, in K, now K moves. She wants to count the number of cells that can be reached in K moves and we need to verify her answer. So we are given a chessboard, 8 into 8 chessboard. We are given coordinates R, C where the king is placed. We need to tell her how many cells can be visited by the king within K moves. So let's look at how to solve this problem. Here we have an 8 into 8 chessboard. Let's just draw that. 1, 2, 3, 4, 5, 6, 7 and 8 and 1, 2, 3, 4, 5, 6, 7 and 8. So let's just number it. These are the rows are numbered from 1 to 8 and the columns also are numbered from 1 to 8. So this is our 8 into 8 chessboard. Now R, C are the coordinates of the king. 1, 3. The king is placed in this cell. So how many cells can the king visit in just one move? K equal to 1. In just one move, how many cells can the king visit? The king can go left, it can go right, it can go down, it can go here, it can go here. This means that these are the cells that the king can visit in K equal to 1 here. So there are 6 possible cells. And which are those cells? 1, 2, 1, 3, 1, 4, 2, 2, 2, 3, 2, 4. These are the possibilities that the king can go. That's why the output is 6. If you remember or recall, we need to tell how many we need to count and tell the number of squares that can be visited or reached by the king in at most K moves. So in at most one move, these are the cells that can be reached, these 6 cells. Now if K was 2, however, then how will you approach this problem? Because this cell can be reached in one move, this cell can be reached in 2 moves, this cell can be reached in 2 moves, so on and so forth. I'm not drawing the full thing, but hope you understand that K can be any value. It need not be only 1 here. 1 was the simplest sample case provided to us, where in at most one move, what are the cells that a king can visit. However, if K becomes 2 or any other number, for example, in 2 moves, it can visit here. In 2 moves, this cell also becomes reachable. In 2 moves, this diagonal, if you go, you reach here. So many more cells become reachable if you take at most K moves, because already we have K equal to 1 moves and we are expanding it in K equal to 2 moves. Now there are many approaches to solve this problem. The first approach is a standard breadth first search approach, on this matrix where you solve it. Now we go with the starting position and we have a queue, and we input the starting position to a queue and start inputting the neighbors, and we'll discuss this approach later. One approach is BFS. The second approach is, let's say the king is here. Now, if the king is here and at most one move, how many cells can the king visit? The king can, we just discussed this, the king can go up, it can go down, it can go here, it can go here, or it can go in the 4 diagonal directions also. So this becomes sort of a box. These are the cells around the king that can be visited by the king. If the king is in the center, this box of cells what I have drawn are the cells that can be reached by this king in one move. Now similarly, if I say 2 moves, it is another box around this box. So if I say 2 moves, it becomes another box around this box. One move, and so on and so forth. So this sort of box approach where you have the king, and these 8 cells that you have can be visited by the king in one move. Okay, these 8 cells can be visited by the king in one move, up, down, left, right, and the 4 diagonal. Now, around this, these cells can be visited in 2 moves. You can ask, how is this possible, and how can, say, this cell be visited in 2 moves? Already this was one move where it went up. Again, go up here. To reach here, there are many ways. You can go diagonal, or you can go up and diagonal. It's your wish here. Many ways to go here. Similarly, for the k equal to 3, there is another box around this king. So this is another approach, that the box approach. The 8 cells that the king can visit in one move is this box. Now again, in 2 moves, it forms another box. So on and so forth. Now the third approach to solve this is, suppose the king is at position RC and you want to reach R dash comma C dash. In order to reach from RC to R dash C dash, you first go diagonally. So basically, if the king is here and you want to find out how many moves it will take for the king to reach here, first move diagonally. Okay, from the starting position, move diagonally, arbitrary number of steps. After you come to the same row or column as this cell, move horizontally or vertically, that many positions. So this cell can be reached in two jumps or 2 moves. This is the third approach. We will discuss the breadth first search approach in detail in this problem. Let's move. In this given sample case, our king was located at 1, 3. I have an 8 into 8 chessboard like we discussed. Now, since my starting position is 1, 3, I am going to add all the neighbors of 1, 3. You might ask, what are the neighbors of 1, 3? This is not a graph problem, how to transform it into a standard BFS problem. So, let's say this is our current position of the king. If this is our current position of the king, what are the possibilities that the king can move in one move? In one move, the king can move into these 8 possibilities. Basically, if the king has to go up from row comma column, let's say this circle here, it denotes the starting position of the king given by row comma column indices. Okay. Now, if we have to move up from the starting position, it is row minus 1 column. If we have to move down from the starting position, it is row plus 1 column. If we want to move right from the starting position, it is row comma column plus 1. If this is confusing to you, take an example. If you take row comma column is 1, 3, if I want to move up from 1, 3, what it is? I have to go to 0, 3. But 0, 3 in this grid is not valid. So 0, 3 is not valid. Hence, this means that we need to have an isValid function that after we compute the neighbors, we need to check if the neighbors we are computing is valid within the bounds of the grid or not. And what will this function contain? You will first check if row is between 1, 8. If your current row index value, what you're evaluating, fits between 1 to 8, and your column value is between 1 to 8, it means that you have a valid cell or a valid cell that you're evaluating. Now, when 0, 3 is passed to this isValid function, it has to give the result as false because the row value what I'm evaluating currently is not between 1 and 8. So we will implement this isValid function. Now, if I want to move right from 1, 3, what will be my value? The row value will be same because I'm still in the same row, but the column value will change and become 1, 4. Now, if I want to move down from 1, 3, it will be 2, 3. So the row value will change, column value will remain same. So I suggest you pause the video and convince yourself that these are the 8 possibilities that the king can move. Now, we have a queue. Let's say we have a queue Q, and initially we add this starting cell. 1 comma 3 is our starting cell, and we add 1 comma 3 to our queue. Now we are going to add the neighbors of 1 comma 3. What are the neighbors of 1 comma 3? Like we said, out of these 8 possibilities that exist here, out of the 8 possibilities, there are 1, 2, 3, 4 and 5 possibilities that are valid. Those possibilities for which the isValid function returned true. Now these 5 possibilities can be reached in one move from the starting position. Now this is our initial step of the BFS, and now all of these are in the queue. Now we take the starting element, we take this element of the queue, we pop it out and repeat the process for its neighbors. Now you'll have many neighbors here. And how many moves? For example, from 1, 2, you might ask, can I reach 2, 1? Yes, from 1, 2, you can reach to 1. Why? Because the cell 1, 2 is here, and the cell 2, 1 is nothing but diagonally opposite to this cell. Hence, it can be reached from the king. But how many moves from the starting position did it take for us to reach 2, 1 cell? From 1, 3, it took us 2 moves to reach. First, from 1, 3, you will go to 1, 2. Then from 1, 2, you will go to 2, 1. So you needed 2 moves from the starting position to reach this cell. So for any cell, to compute the number of moves it took to reach that cell from the starting position, you can say moves of cell equal to moves of its parent plus 1, basically. This means that when you compute the neighbors of this and you continue the BFS, what distance will the new cell be at from the starting position? This is the essence of BFS. So this will be 2, because I first went from 1, 3 to 1, 4, and then I'm going to this new cell here. So this will be 2. Now when I compute my BFS throughout and I finish my BFS completely on the grid, now what will happen is I just need to go through my moves array and check for those cells whose moves are lesser than equal to k. Now our k equal to 1. Hence, after building the whole BFS grid, I can just count the number of cells which have the moves less than equal to 1 here. In our problem sample, if you saw, k was equal to 1 here. Hence, here I can just count the number of cells that can be reached in one move. The starting cell can be assumed to be at distance 0. So 1, 1, 3 is one cell, 1, 2 is the second cell, 1, 4 third cell, 2, 2 is a 1, 2, 3 fourth cell, then 2, 3 is a fifth cell, and 2, 4 is a sixth cell. Hence, from 1, 3, there are 6 cells that can be reached. If you take k at most to be 1. So 6 is the answer for this case. Now you might ask, why did we have this x moves and y moves array? Basically, instead of a cumbersome way of implementing, if we just take the, how do we compute the neighbors of each cell? I mean, by looking at it, we can compute this one by one and check which are valid and then put it here. But programmatically, how do we implement it? So we need to, for each cell, there are 8 possibilities, and we need to evaluate these 8 possibilities. For that, we have 2 arrays, x moves and y moves. Basically, for the x positions, -1, then 0, then +1, then +1, then +1, then -1, you put it in an array. Similarly, for the y positions, you put it in an array. Column means column plus 0, basically. So 0 is added. Column plus 1 means 1 is added. This means that in order to compute the neighbors of a cell, we can just say for index in range 8, traverse through the x moves in the y moves array and say the next cell or the neighboring cell will be nothing but your current cell, what you're doing, plus x move of I, and next cell will be nothing but your current cell plus your y moves of I. Basically, if I want to compute the neighbors of current cell, I know I need to explore 8 possibilities. After I explore the 8 possibilities, those possibilities for which isValid returned true, I am supposed to insert them into my queue. So for that, how do I compute the neighbors? I use xmove and ymove array, and I traverse the I in range 8, basically traversing these 2 arrays which have 8 cells. I will say next cell. Basically, next cell here denotes next row. Next row equal to the current row plus the xmove I, which is denoting the xmove value at the ith index. Now next cell or next column here, next column equal to current cell plus y move of I. So simply, if I just assume the starting position to be an arbitrary row, column, here what will be your first value of next row? Next row will be nothing but current row plus x move of I. So what is your current row? Current row is row. So your first value you will evaluate is row minus 1 comma column. The second value you will evaluate when I equal to 1 is nothing but row minus 1 column plus 1. Now the third value you will evaluate is nothing but row plus 0 and column plus 1. Hope you understand why we have this x move and y move array. Now let us look at the code for the approach that we have just discussed. Here we input the starting row of the king, the starting column of the king, and k, which is at we need to compute or count the number of cells that can be reachable from the king from its starting position at start row, start column in at most k number of moves. Hence we input this. Then we have a queue of pairs basically, where a pair is basically denoting a row comma column. Now initially we have to push the starting starting value of the pair. So we push start row and start column. We make a pair of start row, start column, and we push it into our queue. That is our initial queue state. We have two arrays, visited and moves. Now you might ask, moves array we discussed in the explanation. Why do we have a visited array? Now let's say you are from a cell, you inserted one of its neighbors into the queue. Now, for example, let's take the simplest case. You're at a cell row comma column and you inserted the cell right below it into your queue. Now, when you pop that neighbor out from the queue and again compute its 8 neighbors, in its up condition, from that neighbor, when you move up, you will again reach from where you came. To avoid this from going into an infinite loop and to avoid it from again and again going to the same thing, to make sure as a safe case, we have a visited array. The visited array will make sure that before we insert to the queue, we are 100% sure that we have not seen that same cell before. So that is what the visited array will do. So why are these 9 to 9? Because you're using one indexing and the chessboard is from 1 to 8, rows 1 to 8, columns 1 to 8. Hence these arrays are 9 to 9. Now, what is this loop? This loop is nothing but we just set all the values of both these arrays to be 0. Then we have x move and y move array as discussed. Now comes the main part. While the queue is not empty, do the following. First, get the cell that is currently at the front of the queue. Initially, this will be start row, start column. Now, from this cell or node, we need to compute all its 8 neighbors, and those neighbors that evaluate to true after passing it to the isValid function, we need to insert them into our queue. So again, what we do, we take the front of the queue and we pop it out from our queue. Now we have our current row and we have our current column. After that, we set the visited current row, current column to be 1. Now again, why the visited? Because we do not want to again add a cell that has already been visited into our queue again. So we set this cell to be visited because we've seen it now. Then we have a loop. As discussed, we need to compute the neighbors from every possibility. So there are 8 possibilities from start row, start column. Now out of these 8 possibilities, what would be next x and next y? Next x is nothing but current row plus x moves of I, and next y is nothing but current column plus y moves of I. So we computed next x and next y. Then similarly, we just, for simplicity, we make a next cell pair and we make a pair between next x and next y. Now, this is the main part. After computing the neighbors of the current cell which are popped from the queue, we check if that configuration is valid. If that configuration is valid and we have not visited that configuration of next x, next y before, we push that configuration into our queue and set the visited state to be 1, or we have seen this mode. And then we update the moves. Moves of next x, next y equal to moves of current row, current column plus 1. By this condition. This condition is because where did we reach? How did we reach to next x, next y? Next x, next y was reached as a byproduct of computing the neighbors of current row, current column cell. So since we computed the neighbors of current row, current column and reached to next x, next y, the difference between current row, current column and next x, next y is 1. That is why we say that moves of next x, next y. Next x, next y can be thought of as a child of current row, current column. So from the starting position, we know the number of moves it takes to reach current row, current column. Okay, because in the initial configuration, we have set all the values to be 0. So initially for the starting start row, start column, moves is 0. Then for its neighbors, we will set, for its valid neighbors, we will set their moves to be the moves of parent plus 1. And this will propagate throughout the breadth first search. Then what we do at the end, we just have a simple loop and we will traverse through the whole array and we will check if the number of moves to reach that particular I comma j cell is less than equal to k. If so, we update our count and we output our count. That's all this problem is. Now for the isValid function, let me just scroll up. For the isValid function, we just check if our row is between 1 and 8 and our column is between 1 and 8. So hope this was clear. Hey guys, that was it. Thank you so much for watching this video, and if you haven't yet done this, this is a gentle reminder to hit that subscribe button. If you're interested in competitive programming and data structures, this channel is a one-stop solution for you. See you in the next video. Bye.